demonstration video about plug flow reactor experiment. Plug flow reactor model is used to describe chemical reactions in continuous flowing systems of cylindrical geometry. To conduct the experiment, both diluted 0.1 molarity ethyl acetate and sodium hydroxide are fed into respective holding tank. Then, same flow rates of both reactants are fed into reactor. When a constant conductivity is reached, the product from the reaction is collected. Hydrochloric acid is added to the product to quench the reaction, and titration is performed to determine the amount of NaOH reacted. Finally, the experiment is repeated at flow rates of 0.25, 0.50, and 0.80.
This is the process flow diagram for plug flow reactor that we use during the experiment. The manipulated variable in this experiment is reactant's flow rate. The objectives in this experiment is to determine the reaction rate constant in continuous reactor, to study the effect of residence time on the conversion in a continuous plug flow reactor, and to investigate the operation of a plug flow reactor. Saponification reaction between ethyl acetate and sodium hydroxide forms sodium acetate and ethanol, and this is a second order reaction. The formula used to find the rate of reaction and rate constant are shown in the slide.
Now, I'm going to show you the results of this experiment. The table shows is the data analyzed from this experiment. In the first column, flow rate is the manipulated variable, and once the conductivity value show a constant trend, this is where the residence time is recorded. Next, conversion rate constant and reaction rate is calculated from raw data. From the results, three graphs are drawn. First, graph of conductivity versus conversion. In this experiment, conductivity refers to the ability of free-moving ion to conduct electricity, whereas conversion refers to how many moles of product formed from every mole of sodium hydroxide consumed. Based on the graph, it is clear that conductivity decreases when the conversion increases. This is because as the conversion increases, sodium hydroxide consumed also increases. Hence, the concentration of sodium hydroxide decreases. Dissociated hydroxide ion will also decrease. Hence, conductivity decreases. Next is the graph of residence time versus flow rate and the graph of conversion versus flow rate. In this experiment, residence time refers to the time taken needed to process 1 volume of reactor fluid. In other words, residence time is the time for the solution to complete the travel length. Both residence time and conversion show a decline when the flow rate increases. This is because as the flow rate increases, the time for the reactant to stay in the reactor decreases, so the residence time decreases. So consequently, less chance for the reactant to collide and undergo reaction to convert to product. Hence, the conversion will also decreases. Now, I'm going to explain how to calculate conversion rate constant and also reaction rate. Conversion is calculated by using the formula conversion equals to mole of sodium hydroxide react calculated divided by the initial mole of sodium hydroxide in the sample. So in this case, when the flow rate is equal to 0.5 liter per minute, the conversion value is 0.692. Next, from the conversion calculated just now, we can determine our rate constant value by using the formula x divided by tau CA01 minus x. Our result is 14.978 liter per mole minute when the flow rate is 0.5 liter per minute. And from the constant value K calculated, we can determine the reaction rate by using the formula K CA0 squared multiplied by 1 minus x squared. And the result is the rate of reaction 0.01421 mole per liter minute when our flow rate is 0.5 per minute. Okay, so that's all for the experimental discussion. For the next part of the video, we are going to discuss how to use EXP in this experiment. So first question, what is EXP? EXP is an advanced system for power engineering. As a chemical engineering student, when confronted with a large chemical system, you might ask, where do I even begin? Mass balance, energy balance, thermodynamic properties, or reaction kinetics? So this is where the idea of process model is helpful. Aspen will allow you to create your own process model, starting with the flow sheet, specify the chemical components, the operating condition, and with a click of a mouse button, it can stimulate the model. Not only that, it also lists the result, so you can observe what's happening in the chemical species of your process model. So continue and check out how to use Aspen Plus.
Next, I'm going to briefly talk about the steps in simulating our Aspen results. First, we insert the components. The reactants are sodium hydroxide and ethyl acetate, while the products are sodium acetate and ethanol. Then we set the method used, which is Pang-Rob. Pang-Robinson equation of state can be used to compute pressure for real gas and liquid. The general form of Pang-Robinson equation of state is shown in the slide. After that, in a simulation environment, we choose the reactor type, which is PFR. After choosing the reactor, we input the info for streams like pressure, temperature, and flow rate. Then, at setup, we insert the title Simulation for Experiment 3, the input mode as steady mode, stream class as conventional, value phases as liquid only. For the reactor, we chose reactor with specific temperature and set the operating condition at constant at specific reactor temperature, which is 30 degrees Celsius. We also insert the dimension of the reactor. After that, we insert the info for the reaction. We choose power law, insert stoichiometry coefficient and exponent for all components, and insert the rate constant and activation energy. Finally, we run our Aspen and displays our result at stream summary.
After simulating using Aspen, we can get the raw data as follows. The third column provides the molar flow rates for each component in the feed stream, while the last column gives us molar flow rates in product stream in kmol per hour. The results are stimulated respectively at 0.25, 0.5, and 1 liter per minute. Now, let's look at the comparison between experimental and Aspen value. Firstly, we compare by using residence time. Experimentally, residence time is obtained when conductivity becoming constant. However, theoretically, residence time should be equal to volume of reactor divided by the flow rate. Next, in the aspect of conversion, the value is calculated as the same way as experiments. The only difference is that conversion in Aspen is calculated by using flow rates following this formula. And after calculation, we can see that the conversion decreases with increasing flow rate. This can be explained when flow rate increases, the allowing contact between the reactant molecules become less since they're moving fast. Consequently, less chance for the reactants to collide and undergo reaction to convert it into product. Hence, the conversion decreases. In finding final concentration of NaOH, rate constants, and rate of reaction, the calculation method is the same as before. As expected, when using Aspen, final concentration, rate constant, and final rate of reaction increases as the flow rate increases. In error analysis part, the error in each aspect are as tabulated as follows. The error percentage range between 0.6 to 35%. The error might be caused since the temperature is fluctuating due to the experiment equipment problem. For an example, when the temperature was set at 60 degrees Celsius, the temperature fluctuated between 55 degrees Celsius to 65 degrees Celsius. Also, the reactants in reactors were not perfectly well mixed as assumed. Overall, from the graph, the experimental result shows the correct trend as Aspen does. But the experimental value has some deviation from Aspen simulating values. That's all from the videos. Hopefully you will enjoy it. Thank you.